Hello everyone, welcome back to my channel. Today in this video, I'm going to discuss polarography with a detailed explanation of its procedure, factors influencing and applications. Let's get into the video. Polarography is basically an electroanalytical technique which involves electrolysis of a solution containing electroactive species. Now, when you look at the term electroanalytical technique, you can make a better understanding out of it when you split it into two. That is electro and analytical. So we said that this process is involving electrolysis, which stands for electro in the term. And analytical means some sort of an analysis is under progress in this particular technique. Thus, we come to a conclusion that polarography is a combination of two processes, namely the electrolysis and analysis. These two processes are possible only in the presence of an electrolyte or an analyte, which is a solution containing electroactive species. In this case, we have metal ions as those species. Metal ions are having a positive charge because metals are electropositive in nature. So they have a high tendency of undergoing reduction. We know that reduction happens at the cathode. So these electroactive species present in the electrolyte travel to the electrode, which is cathode, to undergo reduction. When they undergo reduction, they are also polarized. Hence, the cathode is called as a polarized electrode. A polarized electrode in polarography can also be called as a microelectrode. This is because we know that micro means small, right? So only a small part or a small piece of the electrode is responsible for reduction, not the whole electrode. Thus, here we see that a polarizable electrode is nothing but the cathode. It also has another name called microelectrode. So you can mention either of these names in your exam because all these three are correct. But when you say cathode, you should mention that it is a microelectrode because only a small part of the electrode is doing the purpose of reduction, not the entire electrode. We'll move on to the next step, which says that of the various microelectrodes available, the most commonly employed electrode is the dropping mercury electrode, which is DME. Here in this slide, I'm going to discuss about the output of performing polarography. Polarography, as I told you, is a mere experiment where certain things are not visible. For example, the application of voltage. You may not see the voltage being applied, nor can you see the flowing current. You can't see the reduction of the metal ions also. But you come to a conclusion that you have applied some amount of voltage and that current is flowing by looking at the measurements that you get from the ammeter and voltmeter that is attached to the cell. By getting these measurements or these values, you plot a graph where current is taken across the y-axis or y-coordinate and voltage that you are applying will be taken across the x-axis or coordinate. When you plot this, you get a curve. This is called as a current voltage curve. This graph can also be called as a polarogram because this is the exact representation of what you are doing experimentally. It is just the output of what you did experimentally, but in the form of a solid evidence. Like you get it on your paper in a graph sheet, you get what you have done experimentally. Since we get a current voltage curve after performing polarography, we can also call this technique as voltammetry because basically here we are calculating the amount of voltage that is being applied and the corresponding current that is flowing across the cell. Due to these reasons, we can very rightly call this technique as voltammetry. In this slide, I have given some basic information about the electrolytic cell. An electrolytic cell generally constitutes a cathode, that is a negatively charged electrode where reduction happens, an anode, which is a positively charged electrode where oxidation happens, and an electrolyte, which contains the electroactive species. In a polarographic cell, the dropping mercury electrode will act as cathode where reduction happens, and a calomel electrode, which is basically a saturated solution of mercury chloride, acts as an anode. This calomel electrode, being an anode, also acts as a reference electrode. Now we have an electrolyte, which will be the analyte containing the electroactive species, which is metal ions in this case, and we are going to apply a voltage of 0.2 volts. This slide shows the two different electrodes used in polarography, namely the calomel electrode, which acts as an anode, which is towards our left, and the dropping mercury electrode, or DME, which acts as a cathode, is present on your right. This slide describes the dropping mercury electrode. So basically, the dropping mercury electrode is said to consist of a capillary tube that is directly attached to a reservoir of mercury. This point is evident from the picture onto your left. The capillary tube is an essential part of the electrode, and there are certain conditions related to its length and breadth or diameter which are to be taken into consideration while making this electrode. So firstly, the length of the capillary tube. The length should be only between the range of 8 to 30 centimeters, not more or less than this. The inner diameter of the capillary tube should be between the range of 0.05 to 0.1 millimeter. This tube is fixed vertically, through which mercury is forced under pressure from the reservoir. The drop diameter should be within the range of 0.1 to 1 millimeter. And finally, the drop time. Drop time is nothing but the time taken for the drop to form completely and detach from the tip or the end of the capillary tube. So this should be between the range 2 to 6 seconds. This slide shows the experimental setup. Here I have given a picture of the experimental setup along with the components present in it. First, we see that there is a DC supply denoted by capital D. This provides the required voltage to the system. Next, we have a potentiometer included in the circuit. This will act as a voltage divider, and the potentiometer is denoted by capital P. We also have a voltmeter, which is denoted by capital V, included in the circuit. This will measure the voltage that is supplied by the DC source. A galvanometer, capital G, which measures the current that is flowing in correspondence to the voltage applied, is also connected. And finally, we have the polarographic cell with its components attached. In this slide, let's discuss the procedure of polarography. I hope all of you have familiarized yourself with the setup. Now we look at the steps that are to be followed. The first step involves the removal of oxygen by passing nitrogen or hydrogen into the polarographic cell. This is done in order to stop the oxygen from producing an oxygen wave, which will hinder the process of ultimately getting the current voltage curve that is required. So this process has to be followed firstly. Next, the cathode, which is the dropping mercury electrode, is connected to the negative terminal of the DC source or the DC supply. And on the other hand, the anode will be connected to the positive terminal. Anode here is the calomel electrode that we have, standard calomel electrode. In the third step, a voltage of about 3 volts is applied gradually by controlling the potentiometer, which in this case is a voltage divider. A point to be noted here is that the applied voltage is given a negative sign by convention only because DME is connected to the negative terminal. So automatically the voltage that you will apply, which is 3 volts, will have a negative sign, which is minus 3 volts. And on contrary, the current flowing across the cell is taken to be positive. Finally, after the procedure is followed, we get a current voltage curve by plotting a graph with current across y-axis and applied voltage along x-axis. This graph that is obtained finally is called a polarogram. Now let's look at the advantages of using dropping mercury electrode. The first point says that mercury forms amalgams, that is a solid solution with many metals. And this amalgam formation lowers the activity of the metal, thereby facilitating the reduction of the metal ion. So the entire purpose or the entire procedure of polarography is based on the reduction that happens at the cathode. Hence, using a dropping mercury electrode containing mercury can initiate or can increase the rate of this process or reaction. The second point says that the surface of mercury is reducible, smooth, and continuously renewed with fresh mercury. This renewal is evident from the fact that we know that the capillary tube is attached to a reservoir of mercury, right? So every now and then this reservoir keeps producing or keeps supplying mercury. So you get new droplets of mercury that are falling into the electrolytic cell. The third point is mercury forms highly reproducible spherical drops whose surface area can be calculated from their flow rate. So this is the mere calculation that they are talking about here. The next point says that the diffusion current in this case is assuming a steady value. So when there is a steadiness or when there is a stable value that you obtain from a process, we say that this process is highly stable or it is instantaneous, right? So when you use a dropping mercury electrode, the value of diffusion current is remaining stable or it is steady. Thus we see that DME is very useful in this process. The last point says that the hydrogen over voltage on mercury is very high and hence there is no risk of evolution of hydrogen while polarographic analysis is carried out in the acidic solutions, especially with metal ions like Zn2+, which requires large negative potentials. Hydrogen over voltage is nothing but the potential difference between hydrogen electrode and mercury electrode. Since it's happening, the reaction is happening in an acidic solution. So we know that if the medium is acidic, there is a high chance of proton evolution because acidic nature is nothing but the ability to release protons, right? We know this fact. Hence, in an acidic solution, there is a high potential or high tendency of proton evolution. This might hinder the voltage current curve or the current voltage curve that we will ultimately get at the end of the reaction. Hence, we should select an electrode whose over voltage when compared to hydrogen, that is in correspondence to hydrogen electrode, should be maximum. That is seen in this case because the hydrogen over voltage of maximum is very high. So there is no risk of proton evolution or hydrogen evolution. Thus we again see that mercury electrode is an ideal electrode for carrying out polarographic reaction. Even though there were a lot of advantages in using dropping mercury electrode, there are many other disadvantages also. So the first point here says that the most important disadvantage of mercury as an electrode compared with more noble metals such as platinum is the oxidation of mercury itself to mercurous ions at a potential more than plus 0.4 volt. Due to this reason, dropping mercury electrode cannot be used as an anode when the potential is more than plus 0.4 volts. So this can be understood if you can recollect the point that I already told you. I said that DME is connected. DME being the cathode is connected to the negative terminal of the DC supply. So the voltage that is applied will have a negative sign by convention. When DME is taken as an anode, it will be connected to the positive terminal of DC. So its voltage will be in plus, that is, its sign will be positive. So when DME is used as an anode, it cannot be used effectively when the voltage is more than plus 0.4 volts. In the next point, the general procedure is being discussed. So in the general procedure, we saw that DME was the cathode and standard calomel electrode was the anode. So let's say this is very much true in the case that we are considering. But if the potential or the voltage being applied is more than minus 1.8 volts, that is, now we are taking DME as cathode. So it will be connected to the negative terminal and the voltage will have a negative sign by convention. So when this negative voltage or the negative potential that is applied is more than minus 1.8 volts, then there will be a hydrogen evolution. Because it's already an acidic medium, so there's going to be hydrogen evolution. But when these conditions are noticed, that is when the potential is more than minus 1.8, more hydrogen will be evolved and this will interfere in the whole procedure. So that's the second point. The third point talks about residual current. The residual current of DME is quite large in comparison to that of the other noble metals like platinum. This again will limit the sensitivity of the polarographic method, or the effective analysis of the analyte given will be affected when the diffusion current is too high. And the next point talks about the area of the mercury drop. This will be constantly changing because we don't know with what rate the drop will form and with what rate the drop will detach itself. So sometimes the drop might be very small and due to some atmospheric changes it might affect the surface tension of the drop, making it fall. In other cases, there might not be any disturbances to the surface tension of the drop, resulting in a bigger drop that is formed and then it will detach. So there can be changes in the size of the drop that is formed. The next point talks about the clogging of the capillary. We told you already that the capillary tube is connected to a reservoir of mercury and it's constantly flowing across the capillary. That is, mercury is constantly being pushed under force or under pressure through the capillary tube. When this keeps happening constantly, there might be some chances of clogging the capillary tube. That is, when the flow is constant, sometimes it will get stuck somewhere. When there's an air bubble or when there's some impurity, by chance, it might get clogged. So this is another disadvantage. The last point is mercury is volatile and toxic. Therefore, safety precaution must be observed. So when you always do a chemical analysis or when you carry out a procedure, we should see if it is not affecting the environment. That's very, very important. It should be eco-friendly. But mercury is highly toxic. Hence, carrying out this procedure using an instrument having mercury, the disposal of mercury might be a problem because it's toxic to the environment. This slide explains the factors affecting the current flow. There are 4 different factors, of which the first one is migration current. So before I go into migration current, let's get a clarity. Current is nothing but a flow of charged particles. So this has to be kept in mind because when there's always a movement or a flow of charged particles, current will definitely be measured in that place. So let's see what migration current has to do with this case. Migration current is created by the movement of charged particles in the electric field due to a potential difference between the anode and the cathode. So this is also a current where the movement of particles are noticed, charged particles are noticed, but the criteria here is this happens because of the potential difference between the cathode and the anode. So that is migration current. Second one is convection current. This refers to the movement of particles due to difference in density and temperature of the solution. The solution is nothing but the analyte that you are taking. The third one is diffusion current. Diffusion current arises due to diffusion of particles, which are in turn caused by the concentration gradient between the surface of the electrode and the bulk of the solution. Surface of the electrode, nothing but the surface of the electrode, the cathode and the anode that you have chosen, and the bulk of the solution is the electrolyte. So if there is a concentration difference between these two, then diffusion current can be noticed. The fourth and the final one is residual current. Residual current is a result of the combined effect of condenser current and Faraday current. Here we see that a polarographic technique is one that involves the measurement of diffusion current only. Thus, all the other currents, that is the rest of the three currents that I discussed, are to be eliminated as far as possible. First, I would like to explain what residual current is because I did not do that in the previous slide. Now I'll explain residual current and we'll see if residual current can be eliminated or not. So let's just imagine an electrode is coming in contact with an electrolyte. When this happens, there is an electrode-electrolyte interface. This interface is usually called as a double layer because here one layer will be the electrode layer, the other layer will be the electrolyte layer. If this layer happens to be fixed, then it is called as an electrical double layer because it will start behaving like a parallel plate capacitor or a condenser. When this behavior is seen, we can assume, or it is evident, that when you apply some voltage from a DC supply, there will be some amount of current flowing through the two plates that are present, that is across the double layer, and the current that is flowing in correspondence to the voltage applied will be directly proportional. This current is called as condenser current. That is, there's a double layer that is formed, and in that case, when you apply a voltage, a small amount of current will be flowing through the two plates of the capacitor. And this current is also known as the condenser current. Further, a small amount of current will also result due to the reduction of small amount of heavy metal impurities. These heavy metal impurities will be present in the distilled water that we use. To make or to prepare the electrolytic solution, we use distilled water which may be contaminated with some heavy metals. So these heavy metals have a natural tendency to get reduced during the electrolytic process or the electrolysis. So this reduction can also account to some amount of current flow, and that current flow is only called as Faraday current. Thus, as a result of condenser current as well as Faraday current, we get the residual current. Residual current cannot be eliminated. A correction must be made for the residual current in order to obtain the true diffusion current of an electroactive material. Let's look at the elimination of convection current. Since convection current is mainly due to the difference in density and temperature of the analyte, we should keep the cell on a solid support that is free from vibration. Or otherwise, the analysis has to be conducted without stirring and maintaining a uniform temperature. When these conditions are followed, we can easily avoid or eliminate convection current. The last one is elimination or suppression of migration current. Here there is a note of doubt as to whether migration current can be completely eliminated or if it can only be suppressed. So it's always safe to write elimination or suppression of migration current. Here again, we know that migration current arises due to the difference in potential, and it can be eliminated by making use of an extra or excess supporting electrolyte, so that the ions present in this electrolyte will carry essentially all the current that is due to migration. The excess electrolyte is chosen in such a way that its concentration is between 50 to 100, and that it does not react with the analyte under study. So when these criteria are satisfied, we can easily say that migration current can be eliminated or suppressed. And some examples of the excess electrolyte are KCl and KNO3. These are ideal electrolytes. So after eliminating the other three currents or suppressing the other three currents, we are left with diffusion current. This diffusion current can be measured using the Ilkovic equation, which is given as I suffix d is equal to 607 n capital D power half m to the power 2 by 3 t to the power 1 by 6 and capital C. So the term I suffix d represents or refers to the average limiting diffusion current, and it is measured in microamperes. N refers to the number of electrons that are involved in the reduction of 1 mole of the electroactive species. Capital D is the diffusion coefficient, M is the flow rate of mercury, T is the drop time in seconds, and C is the concentration of the electroactive species. Before we move on to the applications of polarography, let's understand two concepts or characteristics of polarigram. So the first concept is the concept of half wave potential, which is indicated by capital E suffix half. This is a characteristic feature of polarogram where it shows the potential at which the current is equal to 1/2 of the diffusion current. So I'm showing a picture of the graph where you can see the half wave potential. This half wave potential will vary from one electroactive species to another. So this is only going to help us understand the applications of polarography. The next one is the occurrence of polarographic maxima. The current voltage curves that are obtained with dropping mercury electrode are distorted by the occurrence of maxima or peaks. These maximas vary in shape from sharp peaks to round humps and are reproducible. The removal or suppression of maxima is very important as they interfere in the measurement of true diffusion current. So maxima can be eliminated by the addition of organic surfactants or surface active agents like gelatin, agar-agar and methyl red. These surfactants are known as maximum suppressor. So the graph will show you the sudden fluctuation or the sudden peak that is arising out of nowhere and the disturbance that it causes. So A is the peak and B is the normal curve that we should obtain. Now let's discuss the applications of polarography. First is the qualitative evaluation of polarographic data. Here in qualitative analysis, we check the quality of the substance or the analyte given to you, where you identify the different ions present. If elimination has to be carried out, we eliminate the interfering radicals and we do the confirmatory test and so on. So this is how qualitative analysis happens. Now, how can you identify the ions present in the analyte using polarography is the point here. I already told you that each ion will have a characteristic half wave potential. So when you come to a conclusion, you can say that the half wave potentials for separate ions in a solution can tell you what type of an ion is present in the analyte. Thus, polarography is one of the easiest methods of qualitative evaluation. The next one is the quantitative evaluation. In quantitative analysis, we check the quantity, or we check the amount of analyte present, we check the number of moles of solute and the solvent that is present. This is what is done in qualitative analysis. We see that the principal use of polarography is in quantitative analysis. Since the magnitude of the diffusion current is proportional to the concentration of the analyte, the height of the polarographic wave will easily tell you how much analyte is present. Since concentration and the diffusion current, the magnitudes of concentration and diffusion current are directly proportional, just by looking at the height of the polarographic wave or the curve, you can say what amount of analyte is present. Thus, polarography is very, very important and also very essential in the case of quantitative and qualitative analysis. So I'm done with today's topic. I hope all of you understood and enjoyed learning about polarography. Thank you so much for watching my video. Please do show me your support by subscribing to my channel, and this will definitely help me and encourage me to come up with new videos in future. Please do like, share my channel, my videos, and also press the bell icon for more updates. Thank you so much for watching once again.